Hello everyone, my name is Hunor Laczkó, and I will be presenting our work called a Generative Multi-Resolution Pyramid and Normal Conditioning 3D CAD Draping. This is a quick overview of the presentation. I will start by introducing the motivation of this work, followed by the challenges that it presents. Then, I will explain the method that we used and the results that we achieved. At the end, I will finish with a short summary and the known limitations of our approach. 3D garment draping is the task of realistically placing a digital garment on a post-human body, making sure it looks natural, with lifelike wrinkles, and conforms well to the body's movements. This can have many applications in many different industries. The most notable ones are the fashion industry, with applications in virtual try-ons and online shopping, and the gaming industry, where it can be used for virtual reality and traditional video games as well. To solve this problem, we have to overcome several challenges, such as being able to generalize over a wide variety of garment types and styles, along with a wide range of movement. For a given pose and garment, we can have multiple valid solutions because of changing dynamics, so we have a one-to-many problem. We should also avoid high computational needs and expert knowledge requirements, which are often needed for traditional physics-based approaches. Lastly, our results should be interpretable for better understanding the method. To overcome these challenges, we propose the following contributions. A pyramid variational autoencoder architecture based on a convolutional network backbone working on 2D UV maps, using vertex normals as conditioning inputs for improving fidelity, and we show that we can achieve state-of-the-art performance like this. For our work, we use two public datasets. First, we use a subset of Cloud3D, which is a large-scale synthetic dataset with a large variety of garments and poses. The second dataset is CAPE, which is smaller, but it is created by 3D scanning real subjects. It still covers a wide variety of movements, although it has less variety in garments. It is also the original SMPL resolution only, which is lower than that of Cloud3D's. We need to prepare these datasets to be able to train our models. First, we transform all pose meshes to a canonical space by unposing and unshaping them by reversing the SMPL scanning process. Then, we convert all 3D meshes into 2D UV maps. For this, we define a mapping between the SMPL vertices and the template UV map, then apply this on all garments. We define two such templates, one for non-skirt and one for skirt-like garments. As part of this process, we also calculate the normal vectors for each vertex and convert them to UV maps as well. Notice how visible all wrinkles are on the UV maps. Lastly, we downscale all UV maps to lower resolutions. To be able to later upscale these without any artifacts, we train a small CNN to help with the upscaling. Now, we can look at the model we are proposing. We use a variational autoencoder to be able to handle the one-to-many problem. To be able to control the generation, we define three conditions: the template garment, the desired body pose, and the normal maps, all which will guide the generation process. These conditioning inputs are encoded with pre-trained encoders, and all features are concatenated with the latent code. This gets passed to the decoder that outputs the desired garment in the canonical space. By stacking multiple versions of this module, we can build a multi-resolution pyramid model. First, we take the base module operating at a low resolution and predict the low resolution version of the pose garment. This has all the major deformations already, but no finer details. We upscale this to the resolution of the next level. The next level predicts offsets only, which are then added to the output of the previous level. We repeat this until we reach a high resolution output. At this point, we convert the UV map output to a 3D mesh. We apply the SMPL skinning and shaping and get the final pose garment. With this, we can calculate the regularization losses, which are the 3D reconstruction, edge, collision, and normal loss. Until now, we use the normal maps of the desired output as inputs, but these are not available at inference time. Fortunately, predicting these is an easier task and can be achieved with the same architecture as the base module. Sampling the latent space with the same conditions can result in realistic and still varied outputs, as demonstrated in this image. With this proposed method, we can achieve high-quality results as shown in these images. In these pairs, on the left are the ground truths, and on the right are predictions. To analyze these results better, let's look at the ablation studies. We performed several experiments to validate our proposal. First, we defined the baseline, which is a single base module at full resolution. Next, we have the pyramid where each level is trained separately and incrementally. And finally, we have the outputs of the end-to-end training of our final model. As you can see, each level of the pyramid adds more details to the previous one and corrects some of the errors as well. Since we have a variational autoencoder model, we can sample the latent space and output multiple predictions for the same input conditions. These show variable results by staying realistic, as we expect them to be. We compare our method to some recent works using the Cloud3D dataset. In the shown examples, we can see that both DeepPSD and Hood can output reasonably good-looking results, but they are not entirely realistic given the input conditions. Quantitatively, we are able to achieve state-of-the-art numbers in reconstruction accuracy. But as we said, this is a one-to-many problem, so evaluating only based on the ground truth is not enough. We also compare some qualitative metrics, like the percentage of collision in the mesh and the change in the surface area of the mesh. While Hood achieves slightly better collision ratio, our model closely follows it, and it's better at preserving the input garment template as reflected by the lower surface area change. We also compare to CAPE, using the dataset with the same name. This dataset is smaller and lower resolution, so the outputs are slightly less detailed. As you can see, we can outperform CAPE with a 3-level pyramid. We can also notice that having too many levels, especially with the low resolution data, can lead to overfitting. In summary, we provided a state-of-the-art solution for 3D garment draping using a multi-resolution pyramid architecture based on convolutional networks. For this, we used UV maps and showed that adding vertex normals as conditions improves the quality of the output. Due to the approach we used, we have some limitations. We depend on the registration of the garments to the SMPL body, and consequently on the quality of this registration. At this point, we are also unable to handle overlapping garments that form multiple layers of clothing. Thank you for your attention. Please check out the project webpage and the paper for further details, and feel free to reach out to me if you have any questions.